audio of your speaker that you want to imitate, right? That 3-second audio also goes as an input. Okay. Now, this text first gets converted to phonemes. Okay. So, what is a phoneme, first of all? To give you an example, right? Basically, if you take the word talk, right? You take this word talk. Talk, the spelling of talk is Talk, right? Now, if you just join together these sounds for T, A, L, and K, right? That's not how you pronounce talk, right? The L is kind of missing, right? You don't see the sound of L in the when you pronounce the word talk. So uh, there is a phoneme conversion of this word talk, and that if you just Google, right? You just say talk and ask Google to give me the phoneme representation of talk, it will say Taak. So Taak, if you pronounce Taak, that is basically talk, right? That's how we are actually pronouncing the talk. So there is a difference between how we write a word versus how we pronounce a word. Okay, that difference uh, is what we are trying to address with this phoneme conversion. Okay. Now, phoneme conversion will convert into phoneme, and you can get the phoneme for, pretty much even dictionaries. I think many dictionaries give the phonemes for all the words. So you get the phoneme. So this goes as one of the inputs. Now, this audio, right? Audio also gets encoded. Okay. So this is the main beauty, what I found in this paper, or this is what excited me the most. I found very surprising. So you need to see some of the history. So this gets encoded and goes, as one of the inputs. Then their neural codec language modeling. This is the VALL-E, right? This is their actual model, what they have developed, and that generates an vector representation of the output audio. Okay, and that goes through an audio codec decoder, which is basically the inverse of this, right? This encoder, the inverse of that, the decoder portion of it, that goes into here, and that generates your personalized speech. So this is the final output that comes. Okay, so basically you have a text prompt as well as an acoustic prompt as an input, and the output is the the speech. Okay, so this is the overall block diagrams. But before we can appreciate what these people have done, it will be good to see a little bit of history. What previous people have attempted to do. Okay, so what previous people mostly what they tried to do, most of the works, right? There's a lot of previous works in this area actually, but let me. This table kind of summarizes. How these people have approached it differently. So what other people have done before is uh, when they trying to convert these phonemes to going from phonemes to an audio, right, waveform, they have an intermediate representation. And that intermediate representation in most of the previous works was MEL spectrogram. So MEL spectrogram is basically the frequency domain representation of a waveform. So you take a waveform, if you remember, if you familiar with fast Fourier transform, so you do a Fourier transform, short time Fourier transform, and it will give you a frequency domain representation of that signal. Basically, it is trying to express a signal as a weighted sum of sinusoids. Okay, so you have multiple sinusoid frequencies, and then trying to express a signal as some linear combination of different sinusoids at different frequencies. That's essentially what a fast Fourier transform is doing. So this MEL spectrogram representation is nothing but it's basically taking that frequency domain representation, okay, and then there is this unit of MEL. Basically, this goes by how our ear, right? Apparently, in the frequency range 0 to 100 hertz, we will have we will our ear is very sensitive to each 10 hertz difference. But when you go from 100 hertz to 200 hertz, the granularity of how much you can discern the different frequencies becomes lesser. Then 1 kilohertz to 4 kilohertz, it will be different. So basically, in the lower frequencies, you want to have more levels of representation. As you go to the higher frequencies, you will have lesser it's like the logarithm, you look at logarithm scale representation, it's kind of similar. So MEL has a, one way of representation, and then the MEL spectrogram is very popularly used, or was popularly used, before this work. Okay. In this work, they are not using the MEL spectrogram representation at all. Okay. Instead, they have gone with what is called an audio codec model. And this audio codec model, again, is not a contribution of this paper. They have basically reused whatever the Meta came up with. So Meta actually published a model called N-codec. Okay. I think that is a very fundamental contribution in this space that I think everybody should know, is that is basically the encodec work is basically an audio compression solution. Okay. See, normally today we do audio compression. How do we do audio compression? How do we save the audio files? You have wave format, and then another popular format is MP3. And then there is one open source format, I think OGG something, right? So there's one open source format. So MP3 is very popular. Many of you may be aware of it. So MP3 is supposedly one of the best known codecs for audio compression and representing audio. So what the encodec did was they came up with a completely neural codec, completely with a neural network. If you remember, we looked at the autoencoder paper, right? Autoencoder, we do on variational autoencoders, we look. So this is, I see the encodec work very similar to the autoencoder kind of work, where you take a waveform and you get a latent representation, which is a compressed, you compress it and then decompress it, right? So you have encoder portion and decoder portion, and then you're basically creating a information bottleneck, right? So when you create the information bottleneck, the compression is happening. So that audio encoder they have utilized. So this is the intermediate representation they are using. Benefit of this representation is now you have this, because this MEL spectrogram we all know. I mean, we know what the MEL spectrogram stands for. Okay, frequency, sinusoids, and all these things. Now here, the latent representation audio codec, we don't know what each of those, what are each of those vector coordinates stand for. The physical meaning of it, we do not know. But the neural network comes up with this representation, and apparently this outperforms the MP3 and all other previous compression. If you see the encodec paper, the separate paper, they claim actually very, like 5x better, 10x better than MP3. The file size, that much compression they're getting with pretty much no, difference, perceivable difference in the quality. Okay. So they have used this audio codec as the intermediate representation and condition on this condition on the audio codec, representation, they are generating the final output. Okay. Now this objective function part, I didn't really understand what they actually meant by this continuous signal regression versus language model thing. I think it's how they view the whole thing. And in terms of training data also, what they did was they increased the amount of training data. So the training data they used has like 60,000 hours of training data with 7,000 plus speakers. Okay. So it has, diverse speakers and diverse, each speaker speaks, the accent is different, right? Accent is different, right? So that gets, captured. And even the, the spacing between the words is different, right? Different people have different pauses and all those things vary, right? So such a diverse set is going to help you with that, right? Now this in context learning, what they mean is basically the transformers ability of, with zero shot learning, right? Basically you gave a very, very minimal input of your desired style, and you are able to generate an output of that style with very minimal data, right? So that the transformer is able to capture all that information and then transfer it that in that style, right? So if you go down here, so this is all, kind of some introduction. I think this page 5, gives, okay, this is the neural audio codec model. This is the model of the, this is Meta's work. I think they just tried to recap that. Okay, so this is, you can think of it similar to the the autoencoder concept, but I think it's a little bit different. They have this what is called residual vector quantization concept. I haven't really read that paper fully to understand this, but it seems like they have, if you look at the latent vector representation, right? Let's say first component you take, that will represent some features, and whatever information it did not represent at the core. So it's like at a course level, you represent something. Whatever information is not represented by that, whatever is remaining, right, the residual portion, that get quantized and gets represented as a second coordinate, and so on, right? So like that, they're getting this latent vector. That's kind of high level. That's the understanding I have. Now, this they're just explaining here in this paragraph how this neural encoder representation is much better compared to the previous, or various other types of representation. Like, there was Hubert and so many other representations, that codecs that came. Compared to that, the Meta's encodec has kind of outperformed everything. That's what they're saying. Okay, so basically, if you look at the here, for example, they give some example here. If you take a 24 kilohertz audio, okay, and what they're saying is this encoder, that is the Meta's encodec, right? This is the big work. It produces embeddings at 75 hertz. So look at the how much compression, right? That is a 320-fold reduction in the sampling rate. Okay, and then each sample, right, is getting modeled as a residual vector. Okay, this is what the residual vector quantization. So basically, right, to give you an example, if you take a 10-second waveform, okay, if you take a 10-second audio waveform at 24 kilohertz sampling, that will be represented by a matrix. Okay, that matrix will have 750 rows, and each row will have 8 columns. Why 750 rows? Because you have 75 hertz sampling, and then it's 10 seconds. So 75 samples in every second. So 10 seconds will have 750 samples. And then each sample you are representing with the eight dimensional vector. So there's 8 is the number of quantizers that they have. So it's very, so the bottom line is it's a very efficient vector representation that can basically represent, an audio waveform, right? So now coming to the problem formulation, the VALL-E paper, what they're doing is, so this is the key point, okay? So their data set that they use for training is pairs of X and Y. What is X? X here is the phoneme transcription, okay? So this is the phoneme, that is the X, and the corresponding audio sample, that is the Y, okay? Now, now this when they get the input, right? So they have this 7,000 plus speakers audio data, right? So what they do is they take the 7,000 plus speakers, the audio, all of that, they transcribe it. So they convert that speech to text. Okay, so they have the corresponding text now. They have the corresponding audio now. Now from the text they can convert to phoneme. So that translation. So you have now phoneme and corresponding audio, those pairs you have it. Okay, so X and Y, this is your training data. Okay, now let's look at what they are actually doing here is, this is the key thing. Okay, so what they are doing here is they take your acoustic prompt, run it through this encode encoder, and that will produce a matrix, right? And that is your what do you say, equivalent of your text prompt in large language model, right? In large language model you have a text to prompt, right? Like that is the equivalent condition on that. So you are basically what you are trying to generate as an output is they are trying to generate the latent vector representation of the output. Okay, let's call that C, right? And given X is what? Your phoneme representation of your text input. And the C tilde, what is C tilde? This is your latent vector representation of your speaker identity, your 3-second, what style you want, right? That speaker. So given these two, X and C tilde, you are generating the C. C is what? C is not the audio. C is just the latent vector representation of the output audio. Now, how do you generate the output audio? Just run the decodec, right? The decoder of the you run on the C, you are going to get your output audio. So this is basically what this is the problem formulation. Now this is what their neural network is finally their model is trying to do. Okay. Now this is how they've implemented that. They have done it with a mix of auto-regressive as well as non-auto-regressive. Okay. So what they're doing is that C vector, right? That C vector has different coordinates, right? So the first coordinate that they're saying, that is the first coordinate quantizer, okay? That they are saying is an auto-regressive decoder, okay? Whereas the following, these remaining quantizers, that is non-auto-regressive. So the remaining ones are non-auto-regressive quantizers. So this part I didn't fully understand, what, so what I understand as auto-regressive is something is auto-regressive if it depends on the previous value. Non-auto-regressive means it doesn't depend on the previous value. So, but finally, right, you are basically getting the output as a latent vector representation, and then you use this decodec to generate the final audio. So, yeah, I think the strength of
so Shindar,
how.
just
Yes.
sorry to interrupt you. This
Yes.
is actually very basic. So imagine that you have the input text phoneme sequence, right? You have the phoneme sequence. Now you have the 3-second voice or whatever, the voice of the person, and you have encoded it, right? And you get the basic quantized, you get those tokens, the equivalent of what would be in a language model, the tokens of that. You feed these two jointly. These two jointly now go into the decoder. So the decoder will start by emitting the first token. That token is still in the latent space. It will later on get decoded into a voice, right? But you realize that, but if you just, for example, forget the decoding part, whatever was said, you realize that the next thing that will be said is conditioned on what has been said, very much like in a language model. The next word you produce depends on the previous word. And that is the only meaning of the autoregressive, that you feed it to produce the next word. You take the original text as X, you take the encoding of the voice, the extrasender's voice, which is also fixed. But if both of these things are fixed, how in the world would you generate the next token? The only way you can generate a different token is if you can take the previous tokens that you have generated and feed it also as an input. That's the autoregressive.
Okay. So it seems like the first coordinate alone, they're using autoregressive, which means in the latent vector representation, first coordinate is autoregressive, but then the remaining coordinates are not autoregressive. So that they depend on, maybe that depends just on the first coordinate itself. Yeah. So I believe they probably did this to reduce the complexity, because if everything is autoregressive, it's going to be more computations. Yeah. So that's what they have done, and I think their strength is basically the size of the training data. That zero-shot learning, they're able to do because of the size of the training data and also the efficient representation, the latent vector representation of the encodec model. I think that strength they are utilizing here instead of building their own. reutilizing Meta's work, which has been trained on even more larger set to capture audio in the best possible, compressed form without lacking or compromising the quality. Relying on that has given them a big advantage here. Yeah, that's pretty much what I wanted to cover.
I think I'll have to read also carefully. I don't understand this part about only the first coordinate being autoregressive. Maybe we should read it again. Nice. Continue, please continue.
Yeah, that's pretty much it, Asif. So then they go into results and they show that how their model is superior in the zero-shot learning compared to all the previous work. So it outperforms all the previous work. I think this paper came only in 2023. That is, this year only this paper has come. So it's a pretty recent one. So the interesting, I was just trying to see like what will it take to train such a model, and they have mentioned 16 NVIDIA V100 was used. That's a lot of NVIDIA V100s, but I'm curious how this maps to 4090. Can 4 4090s do this? I don't know.
See, no, 32 GB, right? None of our 4090 even has 32 GB. It has 24 GB. But having said that, I would imagine today's world, we could do it. It will just take a long time. On our 4090 inference server, maybe. But it will take a long time.
Okay. Yeah, it's pretty amazing that with just 3-second audio, the latent vector representation of a 3-second audio is able to represent the accent with which I'm speaking, the pitch with which I'm speaking, the tone with which I am speaking. All of that is captured in just 3-second audio is what, according to that, 75 into 3 into 8. That's it. 75 into 3 into 8. So many numbers is enough to represent. 10 seconds was 750, right? 3-second only audio they're asking. So 75 into 8 into 3.
Yeah.
So many real numbers represent, basically captures everything of how I speak or anybody speaks for that instance.
The uniqueness of their voice is captured there.
Where did you get the number 750?
Yeah, so if you go here, right, that encodec model, they had explained. So if you give basically, if you give a 25 kilohertz input, right, it produces 75. The embeddings are produced at 75 hertz. So if you had 3 seconds of audio, you will basically have 75 samples, and each sample is represented by 8 real numbers. So you basically have 75 times 8 times 3, so many real numbers. So it will get represented as a matrix, which will have 75 times 3 rows and 8 columns. So that's it. That's your acoustic prompt. Yeah. I mean, coming from a signal processing background, what was interesting for me is there is absolutely no signal processing in this whole paper, and yet it outperforms all the works of the people who used signal processing techniques before.
So there was Asif, is it okay to interrupt her?
Oh, yeah, sure.
Yeah, so there's another related work to this called as VALL-E. I don't know if Susinder mentioned about that, where they take a Chinese accent and then English speaker thing, and they're able to convert it into a similar Chinese, I don't want to use the word Chinese English, but English which sounds similar to the Chinese speaker. So that was also pretty interesting to see how they go from the Chinese stops into the English language.
Yeah, that is true. If you go to the website for VALL-E, You will see at the top, there's VALL-E, there's VALL-E X. X is the cross-link, the multilingual encoding.
Yes.
And it's actually the point that Sushinda makes is absolutely remarkable, that such a small bit of information characterizes human voice. There's a bigger lesson here.
And the other one was that he probably mentioned it, but I think I was also reading this paper parallelly earlier. So there was a prosody, I think which captures all the tones and everything in the study. I think this is where it was remarkable, I believe.
Say that again.
I think it's called as prosody. Prosody is the study of suprasegmental features of speech: pitch, intonation, stress, rhythm, and tempo. So what you can do is, some of the other examples that were given over here, people have products where you can go and now in the prompt, you can say, I want a deep British accent of an old guy trying to speak, or a young girl with an American accent. So you can, in the prompt, you can write that and say this sentence. And what gets generated is according to that particular prosody of the speaker.
That's right. 11 labs, and these guys are all doing that. You have all of these voices, and you can, in various cultural accents, and you can give your text, or you can give your thing and it will say it out in this. I just subscribed to that. I think it's 11 labs it's called. The first month is $1. After that, it's $5 a month.
Yeah.
I'm hoping that since I tend to be in public spaces for camera shy, I could instead write articles and it could speak it.
It comes out pretty reasonably good. So I put in some of the generated audio, right? That Suno AI also, which does that.
Right.
It gives you fairly good. They limit only to 15 seconds generated voice.
Yeah. So Sachin, you are presenting on since you mentioned Suno, I trust you are the one doing BARC, right?
I went to VALL-E. I was reading VALL-E. So as part of it, I was going back and forth between BARC and VALL-E.
So who is presenting BARC today? Satyam is saying yes. Anybody saying yes? Nobody is saying yes to BARC. Sachin, it's you. You have to present BARC. Are you game for it?
I was reading VALL-E. I wasn't reading BARC.
So, actually, Asif, I was trying to look for the archive paper for BARC.
No,
I
you
did
can't
not
find it.
locate that one. I see they have released the source code for it. So there is a GitHub repository with the source code. There are very good examples and everything. But the paper is missing.
Yeah, I also had a tough time looking for the BARC paper.
It seems they did not publish as a paper. They thought, okay, I have published the source code. What more you want? So,
We used to BARC Suno in our previous analysis.
Yes. Nice. Okay, so the next in line. So, hey, this is, by the way, Sushinda. I must thank Sushinda. And you can clearly see how well he explains. Many of you probably know that he's an accomplished educator. If you ever want to learn about Wi-Fi, please take his course. And frankly, his course is far more organized. He has created beautiful, 3 blue, 1 brown kind of animations. He has explained his Wi-Fi concepts using beautiful Manim generated animations. It's just amazing. So we all use Wi-Fi. If you want to know how it works, he's there. So, hey, thank you, Sachin.
Thank you, Asif. By the way, just I did not know about Manim before coming to support vectors. So I should publicly acknowledge that everything I have learned and done or used in a lot of it comes from support vectors, and many things even the support vectors, the backend, all the complete course portal was all written in Quarkus, and I did not know about Quarkus before coming to support vectors. So from Asif only I knew there is something called Quarkus, there is something called Java, so I don't know anything. So, but I picked up a lot of the small hints and clues he gives. From that I kind of picked up and trying to do apply it. Yeah, thank you.
Nice. did an amazing job. Check out his website, guys. All right, who is presenting the next one? I think Mosme. So Mosme is going to share her screen and explain the next one. By the way, Anas made a very, very good comment at one point. Anas, would you like to elaborate a little bit more on your comment?
I guess I was talking about the encodec thing by Meta, which is basically what they're doing is they have a GAN between an autoencoder, and that's pretty similar to what they have in image upscaling, where they have an autoencoder and then some kind of generative model in between. So I was
very similar.
Yeah, I was attending this talk where they showed like they had like a GAN and they had like even stable diffusion kind of like a diffusion-esque model between the autoencoder, and it was like really good at upscaling even at really tiny image sizes, because what they do is instead of they figure out, I mean, we can generate the image and then upscale that image. I mean, it's just like better latents, I guess.
Yes. Yeah, no, it's a great point, guys. Thank you for bringing that to us. I mean, see, all of these are deeply related. Remember when we were doing diffusion model, we were remarking at how similar it is. If you look at the unit architecture, it is basically an encoder with residual links to the decoder, right? And it's sort of a encoder-decoder with a latent, the decoding part is the super resolution aspect of it, reconstructing higher and higher resolution. And in some sense, diffusion model is an encoder-decoder with a in between these little steps of units sandwiched everywhere and attention sandwiched everywhere. So, yeah, it's good. It's good. Actually, if you have that video, could you send that video? We'd all like to.
It was from my university lecture.
Oh, university lecture. Okay.
Yeah.
Nice. So yeah, very interrelated ideas. Mosme, please get started. I'll just put on the screen the lecture. Sure, sure. And you're doing a different paper or the same one? Tortoise, yes, good.
Hi guys, can you hear me okay?
Yes.
Yes. Cool. We heard about tortoise today from Patrick and started reading this paper. I'll go over what I understood from it, and feel free to stop and ask questions. So basically, this is fairly recent paper, as you can see, May 2023. It starts by the thing that I found interesting is this guy says that with the recent advancement in the image generation, as you can see in the field of image generation, has revolutionized the application of autoregressive transformer and DDPMs. And he combines those approaches. So he heavily relies on the existing approaches of DALI and DDPMs for this paper. And of course, autoregressive encoders as well. This is an expressive multi-voice text-to-speech system. So he starts by saying what Susinder said, most modern text-to-speech system operate on speech data that is encoded as a mere spectrogram. And then he gets into how we use image generation using DALI, showed how autoregressive decoders can be applied for text-to-image generation. So we read this paper a while back. Then he talks about DDPMs. So denoising diffusion probabilistic models have recently arisen as the first type of generative model capable of producing crisp, coherence, and diverse images. And they've been quite effective at using low-quality guidance signals to reconstruct high-dimensional space. So what he says is that traditional approaches to DDPMs relied on fixed output shapes that are known before sampling, and then it's sampled from over multiple iterations. So these are some of the limitations, right? He says some of the limitations of DDPMs is it cannot learn to convert text to audio signals because they cannot solve the implicit alignment problems. He also relies on this re-ranking, which DALL-E does to get the better results, right? We've seen that in our bootcamp as well. So I found the section 2 the most important one. So here he says, autoregressive models are stronger at conversion between unaligned domains like vision, text, and speech. We all know that. So in this case, he took a text and a conditional clip. So this is the architecture diagram. There are inputs of text and a reference audio clip for the speaker that we need to clone. Flow through a series of decoding and filtering networks to produce high quality clips. Gets into the details of what this autoregressive transformer does. CLVP is something that he built, and then diffusion decoder finally giving out the output. There are actually 5 units in this: autoregressive, CLP, diffusion decoder, vocoder, and then finally the output. And the DDPs operate in the continuous domain, which allows them to model expressive modalities. So how has he gone about applying this autoregressive plus DDPMs to TPS? He goes into the details here. So he takes an autoregressive decoder, which predicts probability distribution for speech token, conditioned on text. Then he uses a contrastive model similar to CLIP to rank the outputs of number 1. So you take, you get the output from number 1, you rank it through a contrastive model similar to CLIP, which he calls, I think, CLVP. And then finally uses a DTP to convert the speech token back into speech spectrograms. So that is basically the architecture. So a unique design choice that he made is an additional input, which is provided to both the autoregressive generator and DDPM that we talked about earlier, right? The total restrict, right? For the majority of the training posture, DPM is trained to convert discrete speech code into MEL spectrogram. He fine-tuned the DDPM into autoregressive latent space, which is pulled from AR model output instead of the speech code. And then the logic is far more semantically rich than the discrete tokens. And then he fine-tunes it. This is so all of this he just talks about what did he do with CLIP. So similar to CLIP, he took the CLIP for re-ranking. The same type of approach used for CLIP can be applied to speech. So what he used is most TTS data sets are simple pairings of autoclip and text. So by training a model on this pair in a contrastive setting, the model becomes a good discriminator for speech.
So in this,
that's
why he takes the speech and makes it into a MEL spectrogram and does the basic CLIP training that you do with images and text.
Yes.
With contrastive use. Okay.
Yeah, and so he trained the contrastive language voice pre-trained transformer with this is what is the CLVP. It has similar properties as CLIP, but serves as a scoring model, which he used for re-ranking the output. He trained to pair discrete speech token with sex tokens so that he could re-rank it. Then he talks about, again, how he trained it, small cluster of 8 NVIDIA, 39 days over a period of 1 year. Gosh.
Yeah. Sushindra, this answers your question, right? Can we do it on 4090s? We can do it. It will take us a year.
Asif, related to this, is there a challenge with latency? I was reading all over the TTS has huge latency issues.
Yes, it is true. It is the one problem that sort of bothers, because the token generation speed is such that if you're speaking, first of all, there's a latency for doing all this.
Right.
Secondly, if the speech is coming very fast, I think there is some concern there too, that I forget what the concern is, but there's some concern. But yes, latency is the main thing in this, all of these things. So for example, people try to do these demos in which you are saying something, but it is coming out in Obama's voice, like that famous MIT demo. But you have to know that it has been pre-processed. It has been done in pre-cooked and then is being played. But can you do it in near real time? That's where the latency comes in.
Yeah, and my question was, I think TTS superseded other WaveNet who were not using auto regressive encoders. Is there anything else which is superseding TTS to tackle this problem? Do we know?
No, things are happening every day. See, I'm not a specialist in this domain. I know enough about it and keep listening to and reading the research papers that keep coming out. Maybe a super specialist will say something, but to my knowledge, the latency issue is still around.
Okay.
Yeah, when I did a quick research on transform with on TTS, tortoise TTS, there was something called tortoise TTS fast or something like that.
That was also a question to the broader group, Sachin or others, if anybody has heard of anything which is superseding TTS.
Yeah,
where he has given some metrics as to the speed and so I haven't looked into it, so can't speak for it.
Yeah. So speaking of inference is the big topic these days, as Patrick pointed out, and as you guys know, right? All this flash attention, and then there's deep speed, right? One of the big thrusts is that, all right, training takes a long time, but is it possible? Because training is once, inference is forever. So how do we speed up the inference times? And a tremendous amount of recent attention has gone to the inference speed up everywhere.
Okay, I'll quickly go over the inference process. So what he does is feed the conditional input and text into autoregressive model. And we saw it decodes a large number of output candidates. Then he uses the CLVP to re-rank them, produce the correlation between speech candidate and text, and pick up the top K candidates. Then he uses a decoder to decode this MEL spectrogram using the DDPF, because remember he's fed two things, the text and the MEL spectrogram. Then he convert to a wavefront using the conventional vocoder. This I did not quite understand very well. I'll have to talk to Susinder maybe on this.
And when Susinder, this is standard going back from MEL's frequency domain to time domain, right? Getting a waveform out of a spectrogram, isn't that? I'm fairly sure that's what it is. Susinder, are you?
Yeah. Yes, I think this paper, if what I understand, yes, it is basically doing the traditional way, going standard from spectrogram to a waveform. Yeah.
Yeah, frequency to time domain. That's it.
Yeah, and when decoding the autoregressive nucleus sampling is used, repetition and softmax temperature. So this is what he showed in the diagram also. If you see here, autoregressive, then the detanking, then diffusion. He does some diffuser, and then he does take that and convert it into the output wavefront. So that's all there is to the paper. That's the main idea. So then the data set that he has used, what are the experiments and conclusion. What I found interesting other than this was he has given some guidance as to the training and the architecture details. If folks are interested, read through that.
Actually,
what were
could you tell me why is he using a vector quantized variational autoencoder? There's somewhere that I saw.
which one?
Just a little bit above, there was a VQVA. Yeah, he's using
Yeah.
a VQVA. You used with that to a similar. Okay, so original VQ by Van it operates on you. Okay, that's it. Okay, I got that. It's just encoded.
Yeah, exactly. So the VQ used with tortoise is more similar to the original. This, it operates on the MEL spectrogram. And then when the large batch sizes decreased reconstruction losses, so he went with the large batch sizes and stuff like that.
Nice.
So he gives some details as to the model shape and the dimensions, batch sizes that he used, right? Similarly for the auto-regressive, here this was interesting. So the AR decoder uses a box standard GPT architecture and generally follows the training instruction from DALI paper. Unlike DALI, only dense self-attention is used. The prompt is assembled as follows. This was interesting where he did a speech conditional encoding, begin token, the special tokens, text token, end text token, begin ML token, the MEL tokens, and end of the MEL tokens. This we are familiar with, right? They use the tokens, special tokens, to designate the text and the MEL encodings. And that's how you put it, like SC, and then we finally go to EM. I'll learn on a separate encoder that takes the MEL spectrogram and then he combines them. But it's a single vector embedding that is placed in front of the attention context. 2 encodings were produced for each training sample, which were averaged together.
And like in all modern practice, learned positional embeddings are used, which is pretty much becoming the norm.
Yeah, learn positional embeddings are used. You're right. And then he shows a graph of this training and how he was able to train. Then the CLVP, that is very similar to CLIP, where he used to re-rank, right? So the original DALI worked by decoding a large number of images, which is used using the CLIP, right? I continued following the lead for tortoise for reasons that will become evident in the result section. Built a simple model that is very similar to CLIP, which I called contrastive language voice pre-trained. It produces the distance matrix for the text and speech pairs. And that's how he ranks it. It's similar to the text encoder, except that uses 2 of them, one for the text tokens and one for the MEL tokens, which makes sense because he had both. Tokens from both encoders were dropped out at the rate of 15%. Fixed positional embeddings were used. Maximum input length was 350 tokens. And for MEL tokens, the length was 293 for 13 seconds of audio. Diffusion decoder. This is the final decoder, right? So it mostly resembles the traditional unit model used for DDPMs, but without any upsampling or downsampling. I did not understand what it means by ups. Why didn't have to do upsampling?
No, this is the standard. Look at the third paragraph. It explains that.
Okay.
Remember, we covered the UNet, right? What do you do in UNet? You sort of convolute over that, and you extract a lot of features, and then you end up with a latent representation, and then you start upscaling it using effectively the decoding part of the unit.
Yes, but he's saying that he did not use that upscaling or downscaling.
In training that, if you, I threw several different architectures and conditions. This includes a traditional unit, the full attention. So he's explaining that the full attention, this necessity is very small. So he is using the unit, right? It most closely resembles the traditional unit model. That's it, but without any upscaling or downs. Yeah, upsampling and downsampling just means that he's not doing any. I suppose Sushinda, is that right? Upsampling, downsampling would be he's not taking frames, like sampling the frames. The voice thing, right? As you're looking at the voice, he's not eliminating any part of the signal. He's taking the whole thing.
I see. Okay.
Yeah.
This I understood, okay, because in this many sample, but there is this is there he goes into the future works. He's given some hints as to what the future works could be. I I have a summary of the key points from this paper. Okay, so it proposes a new text-to-speech system called Tortoise that combines three things: autoregressive transformer, your denoising diffusion probabilistic models, the DTPMs, and a contrastive model for evaluating the quality. That's what is called CLVP or something.
Yes, clip adapted to MEL spectrograms.
Yes,
the CLVP, and then the unit they are using for the diffusion kind of thinking, and then that's it.
Yeah, it uses an autoregressive transformer to generate a sequence of discrete tokens representing the speech spectrogram from the input text, right? And a DDPM that decodes those tokens into high-quality speech spectrogram, and a contrastive model CLVP that scores the output to select the best one.
Right.
Then he incorporates a speech conditioning input, which are the encoder embeddings from the example audio of the target speaker. This helps infer tone and prosody. The prosody was explained a little earlier, right? So that's why he took the audio of the target speaker so that he could infer the tone, the prosody of the speaker.
Right. Nice.
And the autoregressive and the diffusion models are first trained separately. Then the diffusion model is fine-tuned on the autoregressive model's latent space for better efficiency.
Yeah. Actually, there's a review paper I saw, review article I saw, which compared Tortoise and VALL-E and all of these, Bark and all of these things together, showed their strength and weakness. I wish I could pull that up. That would be.
Yeah. And then, of course, he talks about how did he train it. And so his training used 8 RTX 3090 GPUs over 1 year. And he skipped certain amount of data sets, lot of data sets to train it. One good thing was there's actually a tortoise.tts GitHub. You can go there and you can find all the information there. So it's fairly easy to search it. So if you do tortoise voice clean, you'll get this GitHub link. And yes, useful information available here.
Yeah, the best part is completely open source, isn't it?
Yeah, exactly. It's also available on Hugging. That's what I was going to say. It's available on Hugging Face. So if somebody wants to try it.
So Asif, one of the follow-ups I was thinking maybe is a little bit of a double click on prosperity, maybe as a follow-up paper, or if we could deep into that subject a little bit.
Yeah, that makes sense. We should do that. We could do that.
That's all I had to share. Thank you so much.
Thanks. Thank you, Mosmi. This was very, very well done and really creditable that you dissected the paper and understood it so quickly.
I have still a lot of things to learn from you and Susinder on this topic.
Yeah, not from me. Sushinda is the big expert on signals. And as to your question, what is explain the learnable position encoding? You remember that if you go back to the attention is all you need, you remember that the position encoding was via formula, right? The sinusoidal formula, right? So what has happened over the years is people have asked this question, why shouldn't even the position encoding be more efficiently learned? Let the neural network learn. See, even the first word embedding, token embedding, it learns, right? Even before it feeds it into the attention layer. Once you free it up and say, go learn your own token encoding, it learns. So the people ask this question, why not the position encoding should also be learnable? And they found that when you make even that free and say, we are not imposing a rule, go figure it out, it turns out that it learns it quite well. So the new thinking is let the position encoding as well as the token encoding, both of them be learnable. That's all there is to it, as far as I know. Position encoding is a hidden state. Yes, in a way, it is typically done using just feed forward. You're right, as far as I know. You don't do anything complicated. You just sandwich a feed forward and say, what should it be? Its weights. All right. The next in line is Satyam, it's your turn. Satyam, you ready? Satyam. Your turn.
I don't know anything. I'm not good at this.
Try something. Whichever one you
I didn't read anything because Abhi was covering for me.
Okay. Next is Athira. Athira, are you there? Athira isn't here.
Yeah. Hello, sir. This is Athira.
Yes, Athira. Remember, you represent support vectors.
I don't know if I can explain the paper well enough like Sushinder or Moshmiji, but I will try my best. I'll just share my screen.
Yeah, so guys, for reference, Athira is a part of the teaching staff here. She's a teaching assistant, so we have to expect higher standards.
No pressure.
No pressure.
But today is weekend, right? So it's day off, right?
It's a day off. No, by the way, Athira, I'm joking. Don't worry.
So the paper that we are going to discuss here is transfer learning from speaker verification to multi-speaker text-to-speech synthesis. So when we started reading this paper, we realized that we had to read another paper before this, which is WaveNet. That is one of the neural networks that's used within this architecture that they are proposing. And that is something that we'll go back and do. So in this paper, basically, they are describing a neural network system for text-to-speech conversion. And this is the basic architecture that they are proposing. So this architecture basically consists of 3 components. One is a speaker encoder, then there's a synthesizer module and a vocoder. So I'll try to explain these components. So the speaker encoder is basically an embedding model. So it takes an audio and converts it into an embedding. So the reference speaker's audio is taken and it embeds it into a 256 dimension vector. So what happens here is the encoder, it captures the nuances from the voices, and based on those nuances, it embeds that audio signal into a particular embedding point in the space. And then the synthesizer module. So what happens here is, like as Susinda had earlier explained, the phoneme. So the phoneme is basically I'll show this. The right side, you can see for a sentence, this is a big red apple. The sound of each character of the word, of each word, that is basically the phoneme. So what happens here is there's a mechanism here to convert text to phoneme, and these phoneme is passed into another encoder, and the embedding of the embedding that was generated by the speaker encoder and the output of this encoder is concatenated, and it then passes to an attention decoder mechanism where the decoder then generates a MEL spectrogram from this concatenated. I'll just move to this. Yeah. So the attention decoder mechanism then creates the MEL spectrogram based on the reference speaker's audio and the phoneme that was generated from the text. Then the logs, the MEL spectrogram is it goes to a vocoder or voice encoder. This is basically the WaveNet neural network that I just mentioned. So this is a different paper in itself, WaveNet. So it would take this MEL spectrogram and it would generate an audio waveform at the output. So basically, a reference audio is taken in and the text is taken. It combines the two and generates an audio signal as the output. So this is the architecture that the authors are suggesting in this paper. So what I understood here is that the speaker encoder is a stack of 3 LSTM layers of 256 dimension. LSTM is a long short-term memory neural network. And the synthesizer is a tachotron 2 architecture. I really need to go back and learn what these architecture actually is all about. Maybe Asif sir, you can explain more on this. And also, the neural network, neural vocoder is an autoregressive wavenet, which converts the spectrogram into audio waveform. So one of the advantages of this model is that it can do zero-shot identification, generation of voice as well. So even those voices that are not part of the training data set, it can generate it within like a couple of second audio. From that, it can generate the audio from a text. And as part of experiment, the authors use the VCTK dataset and the Libris speech dataset. So it has, so each dataset has so the VCTK dataset has 44 hours speech from 109 speakers, and they use this dataset to use those voices and use this model to reproduce the same audio signals, and then they have their own metrics to compare how the results are, like how natural the results are, how similar it is to the reference audio, and also speaker verification. So if this is a video, the model will be asked to identify which speaker this is. So they use these data sets to run these experiments on this model, and they get a pretty good result on this data, on this model that they're proposing. And also they also bypass the encoder model here. They basically bypass the encoder model here and just use the text to the phonemes part and put that into the synthesizer model. And they found out that even with like a fictitious speaker, like they are able to synthesize a new voice altogether without having a reference to look for the model to look to. So just using the synthesizer and the vocoder alone, they're able to generate a artificial voice. So this is basically what this paper is about. And some of the drawbacks this paper, this model is that it fails to like capture like accent when it comes to like heavily accented the reference speaks audio, or it kind of misses to exactly reproduce those audio. And the naturality, of course, it cannot capture the exact expression or rhythm or pitch as well as we expect. So these are some of the drawbacks that the authors observed with this model. So this is a basic idea of what the authors are proposing with this model.
Yeah, is there a GitHub project? What's the name of the project associated with this paper? So
there's a Google. So this paper was proposed by Google. So there's a GitHub link. Google's GitHub. This is what.
Okay.
Yeah.
I've seen this. It'd be nice. The speaker adaptation. It's part of the Tachotron project, I think.
Yeah. I still need to figure out if they've actually released the full model as like a full usable model that we can download and use. That is something I need to figure out. But yeah, I've seen people
try and search for Tachotron, see what happens.
Sure. I've seen some people like taking individual components and putting together on their own and seeing how it works. So I've seen some people do that for this particular paper.
Mostly you had a question?
Yeah, so speaker verification, I want to double click on that a little bit. One of the things that AI makes really easy is to be able to take anybody's voice, right? And that gets into the fraud and all that stage. I'm thinking, how do you verify if the audio is actually the person speaking or it was generated by AI? Is that something that's doable? Is that what
Masmi is asking a question that with these generative models, the fact that we are all very impressed with the fact that it can imitate your voice, your tone of voice and everything. So the speaker, like, how do you know that it was the speaker really saying it or versus it was fake? So there are models people are creating to detect, because see, at this moment, right, the imitation isn't perfect. So as far as I know, with reasonably you can tell apart. But I think going forward, the more we move forward, even under careful examination, it may not be possible anymore to do that, because these systems are becoming very, very good with time. Even today, to the layman, it sounds pretty real, but I have seen some papers, and obviously I'm not a super specialist in this domain, but I've seen some papers which says you can successfully disambiguate between real speaker's voice versus synthesized.
Yeah, so there are those things, references which were there in the other paper, which was the Microsoft paper, where they talked about building these models which can detect whether it was artificially generated or not. One concern I had with this tachotron thing, when you go, there's no work after October 22. So does it mean that they have given up on this waveform kind of a thing and moved to codec? See, or
see, when you look at the architecture, and obviously again with the caveat that I'm not a super specialist in this. Compared to the model that, for example, Sushinda covered and the Masmi covered, especially the one that Sushinda and Masmi covered, they look far more nuanced than this. If this model's big, I suppose, virtue is that it's a straightforward model. Right? But if you think about it, Sushinda brought to the fore that the encodec is really very powerful, even at compression and representation. And the paper that Masmi presented, the tortoise, brings the fact that it is very much like, if you think about it, it's somewhat like blip. A blip had the contrastive loss function, right? It had an auto-regressive part. Do you remember that? So there is a very vague resemblance to blip in that. And blip, as you know, is a very successful architecture for that space. And in some sense, tortoise has a vague resemblance to that. Those are somehow they feel like more powerful ideas. So I don't know what happened to this one though.
So I have a question. So all these, since the embeddings are based on the phonome, does it mean that it will work good for other languages also? Has there been any mention or anything that has been tried for other languages?
Yeah, so for example, this one, the Microsoft one, remind me the name. VALL-E. VALL-E X specifically does very well in a multilingual context. But going back to the basics of linguistics, yes, languages are best decomposed into sounds, how they sound. Those are the phonemes. And phonemes are a universal concept. Every language can be broken up into phonemes. I think so. May not be true for pictographic languages, but certainly the English, the Hindi, the languages that we are familiar with, their best representation is in phonemes. Like Sushinda pointed out, right? We talk. If you ask somebody how talk spells, it sounds like TikTok, the talk of, right? There's no L anywhere, and so that's the difference between a word and its phoneme.
Duck is the UK.
Duck, yeah. So yes.
But I assume there should still be some language specific training, right? Because when you're actually writing it in the text, there is no translation going on at the input part, which means if I have to sound ra, then I need to know how it is written in English, right? So which means a language specific fine tuning is necessary for these.
Yeah, see, there are, I would imagine so. So, for example, there are many sounds that don't exist in other languages. Tamil, for example, has the sound very. One of the people, in fact, you're teaching, one of the teaching assistant. If you, those of you who remember Kayal, her full name is Kayal Viri. So now Viri has no English equivalent at all in phonemes, right? Likewise, in Urdu, we speak of kaf. Right? There's a ka and there's a bari ka. And for example, my name starts with a big ka, Kamar. It's when people who don't know the distinction call me Kamar. They actually are mispronouncing my name. So yes, I would imagine that language specific training should go a long way in making it more realistic. Any other questions, guys? So the next is Aditya.
Hi everyone, can you hear us?
Yes.
So it's Albert, Prashant, and Aditya in the room. And
what about Madhu and all of those are also there? The remote ones.
I think Jay is there as well on remote, and
Jay.
Haripriya is there as well.
Yes, Haripriya, nice.
Okay, so can you go on the top, Albert, so that we just talk about, yeah. So this paper is neural voice cloning with few samples. This paper talks about using a pre-trained multi-speaker model and how to fine-tune it for new speakers with few shot learning. And it talks about two of the approaches in order to do that, and compares which one is less compute extensive. And this paper also talks about how we can play around with some of the architecture, or I wouldn't say architecture, actually, some of the voice morphing to change from, let's say, male to female voice, or to change accents.
If I interrupt you for a moment. Guys, this is one of the seminal papers. It's been heavily quoted. If you go to archive and see the number of references to this paper or citations, it's huge. So in a way, this is one of those originals that got this whole thing going. Please continue. It's nice that you picked this paper.
Thanks to Prashant for picking it, actually. So this is coming out of Baidu's company, and we just went through a little bit of abstract of what this paper is talking about. It uses Deep Voice 3 as the base for the model, and then talks about how we can go about learning different kind of aspects in the model in terms of tweaking for new speakers. So it talks about two approaches. The first one is the adaptation. If we can go down in this paper. So it first talks about related work. For example, the base model, which was deep voice model. We didn't go through that paper as a reference, but we started with the methods which they talked about in terms of adapting it for new speakers. So the first one is speaker adaptation. And it talks about how we can tweak the model in order to get the voice cloning for new speakers in few shots only. So the first way is it's saying we have our speaker embeddings in our model along with the weights. And there are two ways. One is to tweak the whole model basically whenever we have new data points coming in, that is our new speakers coming in, we either tweak the whole model and recalculate the weights as well as the embeddings, and for the optimality in the model, and figure out what is the best for the model. The other way is just to tweak the embeddings itself and then figure out what happens when we tweak the embeddings and find the optimal embeddings as per the new speakers. That is speaker adaptation method. And the other method it is talking about is speaker encoding. The way we understood this is, instead of training the whole model again or finding the new optimal embeddings, what if we incorporate another smaller model with bigger model, which can predict embeddings given we have some audio sample with us. So if you can go down here a little bit more. So these are this diagram explains these two different approaches. On the left hand side, we have speaker adaptation, in which there are two methods listed. The first one is basically that in the training phase, we have the text and the audio as an input, and the speaker embeddings are getting learned by the model itself while training phase. And when we are tweaking it for our new speakers, there are two ways in which we can do it. The first one is that we tweak only the embeddings, and we basically not tweak, we basically find the new optimal embeddings as per the new speakers coming into our data point. And the other one is not just only the embeddings are getting optimized once again, but also the weights are also getting optimized. So this is speaker adaptation, and this is quite computation extensive because we are changing a lot of weights and embeddings in this process. On the right hand side is the encoding method. Says that we have our training phase as what we did earlier, but also incorporate another smaller model, which is speaker encoder model, which is trying to predict the embeddings given we have some cloning audio as our data points as well. So while we are training our original model, this becomes another, I'll say, additional component in the model to learn. And once we have learned this, given that now we get new speakers, we don't have to find the optimal embeddings again. We don't have to retrain the model once again. And what we can do is we can just predict as per the new speakers what should be the embedding and uses that as an input to our overall model.
Any questions?
Guys, did you get that?
So the way we envisioned this, that let's say we have our linear regression. If we have to explain it to somebody from first year of college, we have our linear equation as, let's say, y equals to mx plus c. So when we get new data points, we don't want to calculate always our parameters of, let's say, m and c. What we can do is we can create another smaller model while creating our first model itself, or training our first model, which can predict that given a new data set comes in, what will be the value of c for us, or the constant. In this case, we are the new data points are new speakers, and the c, or the constant, or the bias, is as per the new speakers coming in. There are different biases for the new speakers. And thanks to Prashant for bringing up that terminology. When we were discussing it, that we were thinking of how we can explain this. This is how we thought of that. Let's think of it, the constant as a biases for each speaker as such. So that's what the crux of this paper is. This is a little bit older paper. This is from 2018. So it doesn't go as per zero shot learning. There are, I think it's few shot learning though. And it is giving us different ways of training our models for new speakers.
One quick question. Why did it need to pass in the speaker embedding? It was already passing the
I think there is a question, but we can't hear it.
We can't hear louder.
Text and audio. So the multi-speaker generative model is trainable. Text and audio is faster.
Again, we can't hear.
Master, you'll have to enable your voice.
I have a basic question on the first screen. You have a text and audio, which I understood. Where is it getting the speaker embedding from?
The speaker embedding is a parameter in the model itself. At the first time, it is trying to find out what the speaker embeddings should be when it is training the model.
But why is the arrow going to the model? If it's trying to find out the speaker embedding, you shouldn't it be the output?
This is the new.
Yeah, the diagrams are not.
Sorry, what was that?
The diagrams could have been more clearer.
Clearer, yes.
The arrows are a little confusing.
We were so much confused by all the arrows over here. So
I'm not the only one.
It took a very long time over here to create the understanding we have, and we may very well be wrong. So
I rest my case.
all right. So
Audio generation.
I think Asif, you're on mute now. We can see you speaking, but we can't hear you.
Okay, so I was saying that this is a really good old paper, and actually there are a couple of good YouTube videos that go over this paper. You guys may consider watching those. I forget which YouTube it is. I'll try to find the link and put it there, but they are there and they are good. This is very good. Thanks for bringing this up. Questions, guys? Any questions for the center? Next, we'll go to Andy's Mountain. Who's there from Andy's Mountain? Andy's Mountain, Praveen? Anas? Anas, don't disappear on me. What are
Sanjay,
you?
Sanjay, sir, Sanjay.
Sanjay. Yep. No, Sanjay is from a different, you're from different team, right? Yes. Okay, so why didn't you present? So Sanjay is going to present next. But what happened to the Andes mountain? The mountain has disappeared.
Yes.
Anas, what about you? I thought you would be making a good presentation on behalf of your team. Dead silence.
Anas is ready actually.
Oh,
can you guys hear me?
Mountain, right? Yeah. Okay. Okay. So actually, Anas and Amrit, they just said they'll go after this, after Sanjay's presentation. Sanjay, it's all yours now.
You can hear me, right, Asif?
Yes, clearly. You can share your screen and go at it. Oh, Haripriya has a hand raised. Haripriya, do you still have a question?
Sorry, this is from the earlier raising hand. Let me lower it. Thank you.
Okay, I'm sharing my screen. Can you hear me? You can see my screen now, sorry.
Yeah. What is the open source project associated with this paper?
I will find that out and see. I didn't see anything, but I'll find that out.
And is it expressive neural voice cloning? Yeah, please continue.
So it's me, Harini, and Sukhpal online. I'm here in the facility, and this is about expressive neural voice cloning. So it's kind of a step beyond just the voice cloning, and focusing more on the expressive aspect of the cloning. Okay, so what we tried to do here, and Harini and Sukhpal, feel free guys to jump in whenever you feel. So we tried to summarize this in form of a PowerPoint presentation here, so that we'll highlight only the points that are important in this paper, and then we'll switch to the paper if wherever necessary. Okay. So while it talks about just the voice cloning also, and then it highlights the limitations of the current voice cloning approaches in the text-to-speech. It highlights basically the lack of ability to control the expressiveness. So, that's the key aspect that this specific paper focuses on. Okay, so while it's able to, the current approaches are able to do able to give very promising results on the general synthesis, they lack in the expressiveness, and they further lack in specific aspects of it, such as the variation in the tone and speaking rate, emotions, etc. Okay, and then they're also highlighting the advantages and applications of those in the modern day animated films. Your expressiveness in the deep fake videos, and translating speeches from language to the other, where you want to preserve the speaking style of the speaker, but just change the language. And so the paper highlights those limitations, and then it further sets the goal to I'm hearing my echo. Are you guys able to hear me?
Yeah, we are able to hear you.
Okay. Okay. So the goal it sets is basically uses the same TTS synthesis, where it wants to use unseen speaker's voice, but it wants to control the style aspects of the generated speech. Okay, and then the approach that they have is condition a model for text, speaker encoding, pitch contours, and these styles of the speech, and then they're also sort of focusing on. Okay, let me put my thoughts together. So they're using an existing model, and then they're focusing on these aspects of the speeches. And they're, once we look at the model here, it will be clear. So here you see that it's very similar to the model that Atira, and also the model that I think the previous paper brought up, where you have a speaker encoder, and then there is the synthesizer, and then you have a converter, which a vocoder converter here. So here you have the target speech here, then there is a text, which is an input. The speaker encoder actually replaces the one in the synthesizer. So these are the big three components here: the speaker encoder, the synthesizer, and the vocoder. Let's take a look at here. So the speaker encoder is conditioned on those styles of the ones that we talked about, aspects of the speech. And it uses something called the global style tokens. So this is a dictionary of these latent styles, and it uses that to train itself. And I get my voice, my echo again and again. So, but what it is doing is it's using that global style tokens to train itself for the style aspect. And then it also trained to discriminate between the different speakers, in the task speaker verification. It technically speaking, you can see here, it's 3 LSTM layers with 256 cells, and it uses, I'll show you further. It uses the male spectrogram in the synthesizer with 40 channels. So let me go to the next slide.
This architecture looks quite similar to the one that Athira brought.
Yeah, it's very similar to what Athira brought actually, but it just focuses on a different aspect of the speech. So again, same Tecotron model you can see here, but the approach here is it uses 2 algorithms. One is what the Tecotron has, and then it combines it with this Yen algorithm, which focuses on the pitch contours and etc. And it combines those two. So you see here in this model, the text, and this is concatenated here, while the contour from here is removed. You use the GST, which is the style dictionary, and all that is concatenated here. So that's what they're trying to explain here. That
you know what this Yen algorithm is? The pitch contour derived using the Yen algorithm.
Yeah, I'll go here. This is one reference here. Let me just go to.
It's all right. It's some way to get the pitch. Pitch is the frequency contour. So
I think they're talking about some frequency estimator for speech and music. So
yeah. So sir, yeah, this paper talks about like how to fine tune some speaker's voice into the text you have actually. So
right.
It's taking apart all the audio components.
Right.
So speaker information, voice contour, which is pitch information, and then as Sanjay said, global GST, global style tokens.
So global
Yeah.
style tokens,
And
I
then
can
yeah,
understand.
and
They
then
could be a British
yeah,
style, and they could be a Punjabi
yeah. So
style.
there are 4 components. You take them apart and then remove the text component and give it your text.
Yeah.
And then on that thing, it will take all other 3 components, impose that, and it will create then the cloning of the voice.
Yeah.
The,
what I'm
I think
saying,
there is a specific, there is a mention about this Yen algorithm. I'll get back that with that.
Sanjay, just a question. This is for Supal. Remember, see, you do a bit of, is it related to when you have a mixer, right?
Yeah.
Remember, we do all this frequency shaping, the
manipulation stuff.
shaping,
Yeah.
that is
And then last
pitch contour, right? That is a form of pitch contouring, isn't it?
Yeah. And I think Sukhpal is, you can talk about that frequency, different frequency bands if you want to.
No. So most of the only the synthesizer part here we see is kind of AI generated. Vocoder is analog part. We can buy, that
Vocoder is a very
Vocoder
simple.
Yeah,
it's common. It's a decoder to convert into a waveforms, that we can listen to. So that's a pretty common part of various models itself. And I think that these other 2 parts are all very, very similar also to other models.
Okay, nice.
The other aspects also these guys, they further go into details here about this is where we kind of ran out of time to. So they talk about the loss function that they're using L2 regulation here to reduce or optimize the loss, and they're also talking about further the work that needs to be done, so sort of future work. So they're also saying that this is some future that it's not up to the expectation is what I get from here, and then there is some future work that needs to be done. Yeah. Go ahead, Harina, you were thinking.
Okay. So the method, can you hear me?
Yes.
So that they're doing three things here actually. They derive the pitch contour using the in algorithm and scale it linearly to have the same pitch as that of the target speaker samples. That is done using the yin algorithm, and then they use the target speaker samples for obtaining the GST embedding for both the proposed model and the baseline tachytron and the GST model.
Okay.
And then they reconstruct a sample from the target speaker. In this setup, we use the text and audio pair of the target speaker, and that is not contained in our examples actually samples, and try to reconstruct the audio from its factorized representation using a synthesis model.
Okay. Nice.
Yeah. And then they use the style transfer also. Similar to the test task, we scale the pitch contour to have the same mean as that of the target speaker samples to retain the speaker specific latent style. So they're trying to retain the speaker's style.
Yeah.
And then they obtain, by embedding and the GST embedding and the rhythm. So they combine all this.
Right. Nice.
So they basically remove this and then concatenate all these three together, and that's essentially
very nice. So what they are saying is that they were happy with the results, or they were not so happy?
They were happy, but they're also indicating that there is some future work that needs to happen on that.
That needs to be done.
Yeah.
So this paper is which year?
2021.
Okay. In archive, has there been a follow-up to this work?
We haven't seen that, but yeah, but they say this paper actually achieves the naturalness, and they conducted a crowd-sourced listening test on AMT and asked listeners to rate each audio utterance on a 5-point natural scale, and this actually came up till 4.11, whereas Tachytron and all came up till only 2.1, 2.5.
Right.
That whole pitch contour to conversion into the attention mechanism, that I think is the most important point.
So this is the base model, a base thing where you replace your singer.
Right.
Yeah. So creating a music song with a different singer singing the same song.
Yeah. Now, Sukhpal, what I find remarkable about this paper is it seems to be the only one using pitch control. And
pitch contour, yes,
if I understand it right, pitch control is, when I'm looking at my equalizer in front of me, right? The first thing you do to get a particular voice is we do all this, the frequency pitch controls.
Yes, sir.
So in a way, it is the first one that takes a learning from real world equalizer and mixer to this models, isn't it?
Yes. So yeah.
It even says, sir, it can detect happy, sad, neutral because of the pitch contours, and it has a control over the expressions, from the synthesized speech.
Actually, that brings up a question: are we focused more on the human emotions, and that should be a key factor?
Should be, yeah, I suppose so. It captures the emotion. Actually, I was just reading a paper that Patrick and I wrote about emotions. How can you bring emotions into it? It just came out last week, I think, or very recently in this month.
Yeah, I think they're also explaining here the data sets that they use to train, and also you can see here that it's NVIDIA 1080 GPU and hardware that they.
This was trained on a single Titan 1080 GPU.
Yeah. Took around 4 seconds per iteration on single Titan 1080.
Nice. Very nice.
So actually, this raises a. I think what I'm trying to get is some more clarification. For example, right, in text embedding, I think we are all pretty clear on what the embedding has words that is on a particular sequence in a sentence, and we have the window size masking and all that. Based on that, we actually get the text embeddings, right? And similarly, image embeddings, like you mentioned earlier also, like in an image, like the image can be broken into components, which are a word for a sentence, which is the entire image, right? So in that aspect, what are the components of this voice embedding? I mean, I hear pitch, and it makes sense because pitch and tone and all these are important aspects of a sound. But maybe this is very fundamental, but what are the key components of the voice embedding?
See, Haripriya, I don't know how to, sir, but one thing I observed, if you go back to old times, right, people used to talk of pitch, amplitude, and timbre, something called timbre, right, of a voice. I don't hear those words used recently. But if you look at these papers that we covered today, there are multiple approaches. The MEL spectrogram is very frequency domain based. Then, and it uses that. And this one goes back to something new, like or rather old, a pitch contour in some sense. And then if you look at the paper that Sushinda brought up, it says that using this work of Facebook, it basically says, let an encoder decoder model, like that model, infer its own latent representation of audio. Let us not explicitly go and do Fourier transforms or go into time or frequency domain. Let it come up with its own abstract embedding. So we see a variety of approaches in these different papers. One likes MEL spectrograms, which is the traditional approach everybody has liked. One comes up and says, no, let's start from scratch and do a full embedding, a full new encoding, and achieves quite a significant good result that beats even MP3. And then this is more along the lines of still having your MEL spectrogram, but adding some pitch contour and other things to it.
Okay, thank you.
So if we generate, say, suppose as if we take sample your voice, and then we basically train it and create artificial voice that should sound like your voice.
Yes.
How would we compare it? I mean, what would be the quality that, how would we compare whether the generated one is close to your voice?
Well, that is subjective. That's why you have all these graders, right? And in fact, we will know on the last day of this boot camp, each one of you will have to show how well you reproduce it, and we'll all rate it. Remember the bootcamp now, the final project is, actually there is one more project that is still there, which is natural language to SQL, but we'll bring that in at some point. Here, the main thing is, but this project that I just released is that create a virtual teaching assistant who can either speak your voice or my voice. You can pick your choice, which one you would like. But if it is my voice, other people will judge, or your voice, other people will judge how natural it sounds.
So I was seeing a lot of reference in that VALL-E and the VALL-E X, where they not only refer to the tone, but the, what do you call, the inherent, I don't know what's personality or the characteristic of the speaker, whether it's happy, sad, or those kind of things, they generate it as well. So you don't want a monotonous speaking voice, because then you immediately know it's not the real person. So they said about statements, questions, like when you ask a question, the voice raises. When it's a statement, apparently it goes down, things like that.
That's right. And it's also about the way we speak. For example, Indians tend to have a more monotonous, more even language. Americans tend to emphasize the second syllable of each word quite strongly. And it's also a very relaxed jaw speech. You know, the lower jaw tends to be far more relaxed than a British way of saying things.
I think that's interesting because these guys are also saying somewhere here that they had sampled British accent in their data set.
Oh.
Yeah, I think that somewhere they mentioned it here.
Is it because these guys are situated in Hong Kong and they speak British English? Oh, no, these are San Diego. How come they went after the British English?
And the other part that what Sachin was highlighting is basically they're also saying here that while they focused on combination of this heuristically derived and latent style, they're also sort of saying that future work needs to be done in this specific style.
Yeah. Nice. In the last month, I suddenly see a lot of flurry of activity around emotions. And it turns out that the transformers seem to understand emotions. They do. And it's now becoming sort of a hot topic. You see papers coming up and so forth.
That's pretty much what we had on
Asif, a unrelated question to this. When you talk about emotions, do you think that reproducing a song by a artist in including the components of emotions, is that something that's also easily reproducible?
I think it will be, we are almost there. See, here's the thing. At this moment, synthetic voice generation, it still can be known. You can tell that it's synthetic. The detectors can pretty much tell apart, but the gap is decreasing. And quite soon, it will be indistinguishable. I think somebody told me that one of the Beatles is dead, and apparently his voice is now being used to render new songs in that Beatles voice.
And okay, I guess I know that maybe if we were to take a song and remove any audio from it and actually remove the singer voice from it, perhaps we may have to filter out anything that's within 20 hertz to 20 kilohertz, right? Or 20,000 hertz from it. But that would also consist of removing any of the components related to the instruments that may be playing in that part. So is there any way to kind of automatically detect the human voice off of the music in the background? Is there like a...
That problem was solved a long time ago. So see, go back to the old cocktail problem, right? Two people are speaking in a bar, or multiple voices are there. Can you break apart from the noise that comes, which is a mixture of many voices? Can you separate out the voices and what each one of them is speaking? It's called the cocktail party problem, and I think it's a solved problem with fairly good results. It can be done. So to tell apart when music is there in the background, instruments are playing, and a person is singing, to separate all of them out is not a big deal.
Okay. Thank you.
We do it all the time, actually.
Asif, one question I have, I mean, we've gone through these papers so many, and then, we see the cost associated with this is so large that becoming it, commoditizing it is probably far, right?
Yeah, that's right. I mean, there's a reason NVIDIA stocks are doing so well. Today the biggest problem is all this AI has created the world of haves and have-nots. Haves are the people in the $1 trillion club, or not even $1 billion club. They're the $1 trillion club companies, and the rest of us are all paupers. We are the have-nots. We are sitting with our 4090s, maybe 4 of the 4090s. That's about like this. Each one of you are sitting at your home machine with a 4090. So we are the paupers. It needs a fundamental breakthrough to solve this compute cost problem. Let's see. That's the most needed breakthrough at this moment, I would say.
Yeah, I mean, one of the things that this paper talks about, right, making it available for, for example, here I have that. voice assistant and, people who cannot speak, it's manufacturing sort of devices for those. But I think things are so far from that.
Yeah, I mean, see, these things have multiple uses, right? There are people who can't speak, but there are also people who can speak comfortably only when they are not in a public place. For example, I am pretty articulate amongst friends, but the moment I feel I'm standing on a stage or something like that, we all have certain degree of stage fright. So imagine, like, none of us, so lots of people have something to say, but they wouldn't say it in a public forum. They would be too scared. But they can write. For example, they can write articles. And so with something like this coming about, instead of just being words on a page, now what they have to say can become, the spoken word in their voice, their emotions. And that voice is captured when they're relaxed, comfortable, expressive, right? Not feeling stage fright and so forth. And then that thing, all their thoughts re-expressed in that comfortable voice. I think it will be a big boom.
Yeah. All right. That's all we had. Harini and Sukhpal, feel free to add your concluding thoughts.
I think that's it, sir. Yeah.
Yeah, that's in a nutshell, sir. Yeah, but I think this paper is the baseline where you can, create your own artificial songs.
Yes, it's good. It's a good paper. Yes, it must be.
Hey, on the same line, I found a very interesting paper. Zero-shot expressive voice based on bits.
Oh, please share it on Zoom. Don't share it on Zoom. Share it on Slack so that everybody can.
Yeah, that's a great one. Mousme, yeah, it's a very good one, sir. Yeah, same thing. Creating it.
Nobody found that paper.
Okay, we are finding. Thanks. Good.
Creating harmonious sounds. You just give it lyrics and it will create a song by itself.
Yeah.
I mean, on the same line as some expressive voice cloning, but using zero-shot.
Yeah.
It's based on something called bits, which I'm not very familiar with, but apparently it is a state of the art.
Yeah. Isn't it just a VIT for speech?
Could be VIT for speech, but this one is zero-shot expressive. Same thing. Okay. Expressive cloning, voice cloning with zero-shot method based on bits.
Yeah. I know my daughter keeps telling me some things that I always forget. She says that music is made up of two parts. One is harmony. Maybe Sukhpal, you know it. And the other one is, what is the other part to harmony? That in any music composition, there are two parts. One is the harmony part and one the other part.
Beats, is it?
Pitch. I'm not sure, not remembering.
Melody, yes, melody and harmony, right?
Yes.
So I don't know if that is relevant. I am practically tone deaf, so
yeah.
Nice, Amrit, it's your turn.
Yes. Anas. Oh, which teams are Anas or Amrit?
Anas and Amrit are going to present. Anas has disappeared. He's scared.
No, Anas.
I was chatting.
We're quietly staying here, Asif. Okay, I guess we can. Do you want to have a go at it? Yeah.
Go ahead. Good luck, Patrick.
I'm not on meeting. Oh, okay. Okay, so we're going to discuss let's discuss let me share my screen real quick. Okay. So this will be a team effort, as if.
Oh, voice box. But didn't we cover that in the class? That doesn't seem right. Didn't we cover it 2 weeks ago?
Did we?
No, Asif.
No, you talked about it, but we did not cover
it. We didn't cover it. Okay, then it's fair game. All right.
Yeah.
All right. No, this is really a good choice because this is really the state of the art, isn't it?
Yes, Asif. So unfortunately, the code's not available at the moment, but Meta released the first generative AI model for speech to text, text to speech, and more actually. So you could go to this site to see on the paper what it can actually do. Where so our group is going to slowly discuss and how we understood VoiceBox, which is based on a new concept, a new modeling concept called flow matching. I think the paper was published also earlier this year. And the nice thing about VoiceBox is it's outperformed already the current state-of-the-art English model, the VALL-E that was discussed earlier for zero-shot text-to-speech. Now, just as, yeah, so just some bragging rights of Meta and style similarity. So the strategy behind it has to do with this idea of flow matching models, which is essentially for diffusion models, we first learned we used some Markov chaining strategies to go from a clear image and to noisify essentially. Now the idea behind flow matching is that given that mapping of probability distribution from your first input to your target, can we map back? So that was where the discovery from the flow matching model is that they're able to find with some caveats, and Amrit can help explain some of the math later. But we're able to revert back, or what was the word they used? Invert. It's invert. It's an invertible model. So you can noisify, but you can denoisify. So now what happens is in VoiceBox is, can we introduce it?
See, the flow matching, this is based upon normalized flow models. And if you remember, did I cover normalized flow models?
No, you didn't.
The Jacobians being invertible determinants and so forth?
No, not yet, Asif.
Okay, so I should cover that because normalized flows is a big generative topic, and perhaps the only topic I missed. I'm going to cover the normalized flow. When should I cover it? We should come up with an idea. Maybe next week I should cover it. Please continue.
Yes, sure, Asif. So for everyone to get on the same page, just to have an idea that from probability distribution to a target probability distribution, it can be inverted back, and adding some kind of mask to infer from the prior and from somewhere within the context of that input is the idea behind VoiceBox. So while inverting, introduce this mask and then revert back. The nice thing about this is because the mask is predictive, the model has been trained, the VoiceBox model has been trained to help predict and fill within was it in context? I forget what was the term. Anyway, to fill in the mask, to learn from the mask, it is able to do style transfers also across infill speech from context. So it's able to learn and infill what was missing or what you had been expecting. So in this scenario, we could do a lot of things. You could do text-to-speech synthesis, or you could do lingual style transfers. You could even transfer accents, and at the same time, clone voices. So I leave it to the rest of the team to the rest of the members in this group to just read through, look through this demo. But after this, I can hand over the floor to Amrit, who can discuss in more depth the actual paper for VoiceBox. So where do you want to go?
Yeah, sure. So I wanted to cover some of the methods that they. Yep, I wanted to cover some of the methods that they describe in the paper. And again, this kind of touches on the subject of or very much touches on the subject of normalizing flows, which is essentially like a model in which, given an initial distribution, Give me 1 second. Sorry. Yeah, given an initial distribution, you're trying to learn, you're trying to approximate an unknown distribution, also known as the target distribution. So for the normalizing flows, there are a few variables, such as the vector field, which is denoted over here, and also the probability path. And so the vector field is moves points from the initial distribution to the target distribution. And you do this by solving this differential equation right here. And the probability path is used to create a time-dependent PDF. And this describes how the data points change over time. So the issue over here with VoiceBox is that they want to train a network to learn the vector field, which aims to make the transform distribution match the target distribution. But in practice, they don't have direct knowledge of the probability path or the vector field, which makes it challenging to compute the loss of the gradient. So the way they tackle this is by introducing the idea of a conditional path, a conditional probability path PT, which is a mixture of simpler conditional paths. And these paths have known vector fields, so it's easier to make the computations for them. So VoiceBox introduces something called the conditional flow matching objective, which is similar to the flow matching, but it, again, uses these conditional paths. So after they kind of formulate the problem, they divide the model into 2 parts. An audio model and a duration model. So they use for the audio model, they are predicting missing audio frames given a context, again using the normalizing flow model. And so the input is an 80-dimensional Mel spectrogram, and they employ a transformer to model the conditional distribution for all the frames. And then they use an embedding and concatenate it with the audio and context inputs. And this is for also to apply a positional encoding for the flow step. And so the duration model, the second part of this is, and Asif, please feel free to correct me if I'm misspeaking about this part, because this part kind of confused me as well. But it uses a conditional vector field to model the distribution. And then you use a masked version of the normalizing flow for training. And so I wasn't sure why they exactly created this mask. But yeah, this is the solution they used.
No, how would you know? You need to do a reconstruction, right? Unless you mask something, how would you do a reconstruction? The mask, like, see, you do a conditional vector field which swaps the excited, right, associated field. The masked version of the loss is used for training. For simple way, you need to look at the forward path, right? Not the. You need to causally. You need. I think so. You need to hide the parts that are in the past. So suppose you are generating a translation of a sentence. Surely you don't want to use the future tokens. Show the future tokens. I think that's the reason, but I'll have to read the paper more carefully. Actually, I don't know. I need to read the paper. I think I used to remember what it was. I forgot. I read this paper when it came out. About a few weeks ago. I've forgotten it already.
Yeah, they also discussed a second solution, which is like a regression-based duration model, and you know that does the predictions given the context and the phonetic transcript. Right. So, yeah, that's there too.
Straightforward, which is straightforward in this. You're basically predicting what it should be. And because these are vector fields, you can vectors, you can therefore look at the regression makes total sense because you're looking at the divergence of what it should be and what is.
Right, yeah.
Mass, when I forget, I'll remember it. I think it has to do with the causal nature of it. Or was it predicting? No, or maybe was it? See, there are only two possible things. One is to prevent look at the causal aspect. The other is to, by masked, you make it a masked language model kind of thing. You make it predict what is it that was masked. I forget what the explanation is. I'll read it more carefully and get back. I think it's in the previous page. If you go back, I vaguely remember that explanation right here itself somewhere. Classic audio model. Yeah, audio model. Go down. Right here, somewhere it says, with the conditional, flow is matching for simpler conditioning. We condition on all frames except of only masked frames. A neural net is parameterized in the conditional vector given. Okay. Per phone neural. I think that's what it is. It's the future frames. But okay, I'll think about it. I'll read it properly and get back.
Yeah, and
the minute that I was speaking about is there in your equation too. You know, that is the classic signature of normalizing flow models. Equation number 2.
Asif, can you turn up your mic just a little bit? You're very quiet compared to the other speakers.
Oh, I am very quiet? Okay. No, I'm saying if you go up to equation number 2.
Perfect, thank you.
Equation number 2. Yeah.
Yeah. So you see that 1 and 2 are the classic things about normalizing flows.
Yeah.
And the determinant I was talking about is the determinant in equation 2.
Okay, I see. Yeah, I mean, so the math was a bit tricky to understand, especially in 20 minutes, but...
No, you don't want to understand. It's a pretty big topic. You don't want to understand that normalizing flow from this paper. You want to read it from a... okay, I'll explain it better. It's a textbook thing. Best understood properly what normalizing flows are, and then coming to this paper.
Mm-hmm. Yeah. But yeah, the results were pretty favorable. Actually, I mean, they said that that the similarity was, if we go to the results section really quick. So they claim that it outperforms the state of the art with a lower word error rate and a higher audio similarity score while being up to 20 times faster.
Yes, yes. I mean, the voice box is practically magical at this moment. It beats everything. And the tragedy is Facebook is getting the same infection as OpenAI. They don't want to release their code or their model anymore. So all we can do is appreciate this paper, be impressed with their results, and then twiddle our thumbs because none of us have access to it.
I think it's in the blog post, actually.
Say that again, Anas, in the blog post?
I was saying the results might be in the blog post. Maybe not. Oh, right there, yeah.
Yeah. No, all the results are very impressive. It seems to be beating the state of the art in everything. But the whole question is, how do we get our hands on it?
So they said it's just, oh, go ahead.
Sorry. So the best that is available for us is enhanced Bark today.
Yes, enhanced Bark.
That is pretty good as a file.
Oh no, Tortoise. Tortoise is pretty good too.
It doesn't do music, right? Because that has, I think, yeah. I tested about Tortoise and Enhanced Bark. Enhanced Bark is much better, I think.
Much better.
Terms, yeah.
Okay, nice. Actually, this voice box can do many things. It can do accent changes and language changes, and it can do multilingual. Like people who come, like for example, people from the Indian diaspora tend to speak, even when they are speaking in Hindi or Tamil or Telugu or whatever language, they tend to mix English with their language. Right? It's a mixture of English and the native tongue. And a voice box, to my knowledge, is one of the best models that can understand these mixed languages and still translate. So it is very good. I wish we had our hands on it. I mean, this actually is a sad trend. If this goes on, soon none of the companies will be releasing any models. These companies have an infinite supply of GPUs. They'll keep making bigger and bigger and bigger models. And you and I will be just sitting there on the sidelines, reading their research papers and getting impressed and not getting to touch these. So it's a pity. Nice guys. It's good that you guys picked this paper. So when I think about it, all the generative aspects, the VQ autoencoder, variational autoencoder was covered. We have a unit kind of concept was covered. Diffusion models were covered. This normalizing flows are covered. When it comes to generative model, the only thing, well, not quite covered, but generative GAN, neural style transfer using GAN kind of model, I didn't see cover. Contrastive loss, clip-based models.
Wasn't that the first one?
It wasn't a GAN. Was it a GAN?
They had the discriminator.
It had a discriminator, but did it have a generator? I forget that.
The generator is the latent in the middle. So it had the autoencoder, the encoder, the decoder, and the middle is like essentially the GAN.
Was essentially the GAN. This is the VALL-E paper, right?
Yeah.
Okay, so yeah, it looked like that. I wasn't sure whether it is really. I mean, obviously the ideas are similar. Actually, I don't know. If it was, then it's good. Then basically people have tried all the generative models.
As if the closest I found for the voice box implementation, somebody tried. So I'm just posting the link here.
There's nothing there actually. the repo is empty.
It's empty, but but some people are trying.
Yeah, that would be nice actually if somebody implement. So the trouble is, even if you implement the code, who's going to pay for the GPUs to train this? Some government, somebody should sponsor this. Actually, I do feel that now the AI model development should be heavily funded by National Science Foundation and the US government before the entire thing becomes an industrial capture of the big giants. What will the research community do? Just sit there and twiddle their thumbs. If you are not in Facebook or Google or Microsoft, you basically sit there and twiddle your thumb. Like OpenAI or so forth. Nice, guys. So this was a wonderful. Did we miss a team? I feel we have missed one team. Which team did we miss? Oppenheimer. Anybody from Oppenheimer still present? Or has everyone dropped off from the Oppenheimer team? Oh, nobody from Oppenheimer is here.
Just two of us. I just updated you.
Oh yeah, your team also. And the other team that is missing is the Transformer team. Transformer team also, I don't see anyone. Okay, guys, so next time we'll start with those teams. But good show, guys. We had a pretty good set of paper reading. So do you believe that it's a good idea? You guys should do the paper readings instead of me. How many of you vote for that? Raise your hands in Zoom. Good, Srinath, one vote. How many of you would prefer this format in which you guys do the paper reading? Only one vote? No votes. Even Srinath's hands has gone down. Okay, let me see if anybody is even listening. How many of you would want me to do the paper reading? Raise your hand.
I'm just checking how to raise the hand. Okay.
Okay. All right.
No, I think this format I prefer because
you prefer this format, right? In which you guys do.
Yes. Yes.
Okay. So we will do that. Next time I'll just give you guys the topic and you guys do the paper reading. And what I will do is I will move my paper reading to the usual Friday afternoon or Sunday evening, one of the two. The public paper reading. Make sense?